Hope you're trying to have a productive day. In this video, we will be going through another K-Pass paper question. This one will be question number 2 from the Physics 2012 paper 2. So without any further ado, let's get right into it. Right then, question number 2, part A. A mass M oscillates on the end of a coiled spring of spring constant K. Write an expression for the period of oscillation T of the mass spring system. Now, I think they should probably reword their writing here for these questions to avoid confusion. It says write an expression, but most people will probably just write an equation. There's a difference between an equation and an expression in mathematics, but maybe the examiners are not too harsh. And if you write an equation, maybe they'll count it as an expression. Anyway, it's not a very long process to write the expression. I would recommend being on the safe side and writing an actual expression. So the equation that you're looking for is an equation that you can derive. I will not go into the derivation of that equation in this video, though I will touch on a little bit of the derivation, just a small bit. So the equation you're looking for, the expression that you're looking for, the equation that it comes from is this equation right here. And this is something that once you learn how to derive it, you should also learn the equation itself, because if you try to derive it every time you want to use it, you might run out of time in certain situations. So you probably just want to learn the actual equation. And you can learn the derivation as well, just in case. So the equation, without any further ado, the equation is this equation right here. T, being the period, is equal to 2 pi times the square root of the mass in the mass spring oscillator divided by the spring constant of the spring in the mass spring oscillator. This is the equation. Now, to write this as an expression, you could probably just get away with this. So T is determined by 2 pi times the square root of M over K. There you go. Moving on to the next question. This one is a very long one. Figure 2 illustrates a block which can be made to oscillate vertically between two identical springs, each with spring constant K. There's a diagram right there. The vibrator has constant amplitude. As the frequency is changed, the amplitude of oscillation of the mass is measured. Table 1 shows the data recorded. Now you can already tell, they're not just going to give you a table to just look at it, right? Dun dun dun! There's a graph. So when you get a table, more than likely you're going to get a graph to plot. No matter what the situation is, make sure that you are able to plot graphs in a timely manner and in an accurate manner. It takes practice, but it's doable. These are the frequencies that the oscillator vibrated at, and these over here are the amplitudes of vibration of the mass, right? Now, what does the amplitude and the frequency really mean? Well, frequency is just the amount of oscillations that happen in 1 second, right? It's per second. Frequency is the inverse of period, where period is the time it takes for one oscillation. What is an oscillation? An oscillation is one complete to and fro movement. Now, this mass spring system is held by two springs, one at the top, one at the bottom, and the mass is in the middle. The oscillation is going to be the spring moving from its equilibrium position, which is when the spring is about halfway between here and here. And then the spring is going to move upward or downward, depending on where it goes first. But let's say for this argument, it moves upward. It's going to move upward, up to a distance, and then stop. And then it's going to move back down to its equilibrium position. Then it's going to pass the equilibrium position and go downward, reach a position downward, stop, then it's going to go back up to its equilibrium position. And then it's going to go up again, stop, go back to equilibrium, go down, stop, go back to equilibrium, go up, stop, back to equilibrium, so on and so forth. It's an oscillation, right? So the oscillation is the one complete motion where it goes up, stops, goes back down, stop, goes back up, and stops at the equilibrium position. That is one oscillation. Right? The amplitude is basically the displacement that the mass makes when it stops, either in the up or down position. Or in other words, the amplitude is the maximum displacement of the mass in the mass spring oscillator. So when the mass goes up and stops, the point where it stops, the distance between that point where it stops and its equilibrium position, that's the amplitude. And when it goes down, and stops, the distance between where it stops when it goes down and its equilibrium position is also the amplitude, but it's a negative of the amplitude because it's in the opposite direction. So you have the positive amplitude when it goes up and the negative amplitude when it goes down. So basically, this variable frequency vibrator vibrates and it causes this thing to move up and down. Then at a different frequency, the amplitudes of the vibration changes, which means this might go up more and stop compared to a different frequency. So if you look at the table, just glancing at it, you can see that at the frequency of 12.5 hertz, the maximum amplitude was gained, right? So the amplitude is just the maximum displacement, but these are different amplitudes. So which one of the amplitudes is the maximum amplitude? It's the one that has the highest amplitude right there, which is 4.6. So when this thing was made to vibrate at 12.5 hertz, it had the biggest amplitude out of all the other vibrations, right? And that right there is a property of vibrations, and we will name that property as we go down in the question. I'm just explaining what happens in the mass spring oscillator. You know, a lot of the times in the mass spring oscillator, it's just one spring, it's not two. So I'm just explaining what it would be like if this looks unfamiliar to you. So down here on the grid on page 7, which is this, plot a graph of amplitude of vibration Y against frequency F. So we're going to have to plot a graph. Let's get into that right now. So I'm going to plot a graph. And like I said in one of my previous videos, when you're doing a graph, you want your graph to cover up the allotted space, but you don't want it to be too big that the values can't fit on it. So your graph should be large enough to cover up most of the space, but small enough to where all of the values can comfortably fit on the graph. Right? How do you determine what size your graph should be? The size of your graph is basically dictated by the scale that you use for the different axes. The scale that you use is going to depend on the range of the values of the information, the data points, and also the amount of space that you have. All right, let me just do the graph right quick. Here I have the graph. Let me zoom out so you can see it a little bit better. So this is the graph, right? So let's say, for instance, you had the highest point on the y-axis as 4.6. And if you go back here, we can see that the highest point on the y-axis was 4.6. These are all smaller. These are all smaller. This is the largest point on the y-axis. The question said plot amplitude versus frequency. So the first part of the title. So the first part, in this case, the amplitude goes on the y-axis. And then the second part of the title, in this case, frequency goes on the x-axis. So the largest point on the y-axis is 4.6. So let's just say the largest point is 5. Let's just say the graph needs to go up to 5. The graph just needs to go up to 5 units, right? So the highest point on my graph is 5 units. And let's say I have 10 graduation marks on my graph paper, right? All I need to do is just basically say, we have 5 that we need to go up to and we have 10 marks. So it's going to be 5 divided by 10. That gives you a half. So each mark is going to be a half of the unit that is going to go on the respective axis. In this case, the y-axis. So right here would be 0.5. This would be 1. Then this would be 1.5. This would be 2. 2.5, 3. So each one of these small marks represents 0.5. On the x-axis, I went up to 21. And let's just say I had, 21 graduation marks, right? So it would be 21 divided by 21, which is 1. So each graduation mark is 1 of the unit, which is why the first graduation mark is 1. Second one is 2. Third one is 3. Each one of these represents 1 unit. And you count going up. So that's basically how you're going to make a scale for your graphs. Hopefully, they don't give you graphs that have really large values and really small values on the same scale, because then you're probably going to have to use logarithms to plot that graph. But for the most part, you'll just get a graph like this. You make sure that the numbers can fit on your graph, and you make sure that the graph is also large and covers up most of the allotted space, right? Before I end on the graph plotting, you're going to want to label your axes. So this, you're going to label it as the y-axis, and you're going to put the name of the units here. And you're going to label this as the x-axis, put the name of the unit. So this would be amplitude in centimeter, and this is the y-axis. And then this would be frequency in hertz, and this is the x-axis. Your graph also needs to have a title, which the question basically gives you the title of the graph. Your graph also needs to have a scale, which is what you use to make the graph points as well. So your graph needs to have a scale, and what your graph needs to have the origin. You can put this as 0. And it's 0 for both of them. There you go. You want to get used to plotting graphs because you're going to get graphs, all right? You can't run away from them. Now we have to plot the points on the graph. So allow me to do that real quick. But just to show you how to plot the point, Basically, you look on the first set of points. So I look at the x1 first, or I look at the point on the x-axis first. So it would be 2.5 on the x-axis to 1 on the y-axis. So I go to my x-axis and I find where 2.5 is, and that is roughly about here. And then I go up until I reach 1 on the y-axis, which is about here. This is the 1. So where the 1 and the 2.5 meet, that's where the point goes. And I use x's to plot my points. Right then, so the graph points have been plotted. Now I have to draw a line. And this line is going to be a curve. I'm going to start from the first point because the instructions did not tell you to start from 0. So I wouldn't start from 0 here in this scenario. And that's basically what my graph looks like after drawing the line through the points, right? It looks something like this, kind of like a bell curve, right? Plot the graph of amplitude of vibration y against frequency. We just did that. Second part of part B. For the block oscillating at maximum amplitude, determine the angular frequency and the period of oscillation. Let's get into that right now. Now the question said at maximum amplitude. So maximum amplitude from the data that we got was when the frequency was indeed, maximum amplitude was when the frequency was, let me go back up to the table, 12.5 hertz, and the amplitude was 4.6 centimeters. The question wants us to find angular frequency. Now angular frequency, represented as omega, is equal to 2 pi over the period. In other words, it's equal to 2 pi times 1 over the period. Now remember at the beginning of the video, I mentioned that frequency is the inverse of period. So right here when we have 1 over the period, the inverse of period, we can basically just replace the 1 over the period with frequency. So angular frequency is equal to 2 pi times the regular frequency. That's what we just figured out, right? So when the question wants us to find the angular frequency, all we have to do is state the frequency and multiply it by 2 pi. The frequency that gave us the maximum amplitude was 12.5 hertz. So it would be 2 pi times 12.5 hertz. And that would end up giving us an angular frequency of 78.5 radians per second. Now the question wants us to find period. How would we find the period? Well, like I just mentioned, and like I mentioned before in the video, period is the inverse of frequency. So frequency is equal to 1 over the period. If you multiply this side by period, multiply this side by the period, we get period times frequency is equal to 1. Now we can divide this side by frequency and divide this side by frequency. Should I cross these out? Cross them out. So basically we get period is equal to 1 over the frequency. So all we have to do to find the period when we are given the frequency is just divide 1 by that number, 1 by the frequency. So it would be 1 divided by 12.5 hertz, and that would give us 0.08 seconds. There we go. Part C. The mass of the block is 0.05 kg. Calculate the spring constant K for one of the springs. How would we find the spring constant? Well, according to Hooke's law, as long as this spring is in the elastic region, right, force applied is equal to the spring constant times the extension. So if we have the force and the extension, we can find the spring constant by just dividing the force by the extension. But the question did not give us the force, and the question did not give us the extension. So we cannot use this way to come about the spring constant. But from this equation, you can derive another equation. And when you derive that other equation, it's going to look like this. It's going to look exactly like this equation here. Period is equal to 2 pi times the square root of m over k, right? So in order to find the spring constant, we can just plug in the values for the period, which we worked out, and the mass, which the question gave, and then we can find the spring constant. But there is an even easier way. You see, when you're deriving this equation here, you come to a realization. And that realization is this. You come to the realization that omega squared is actually equal to k over m. Right? Somewhere when you're deriving the equation, you come to this. And this is the part where I said I was kind of going to touch on a little bit of the derivation, but I'm not going to go too in-depth with it. All you need to know is that omega squared is equal to k over m. So if you want to find k, all we have to do is just square omega and then multiply it by m. And then we're left with k. So omega squared, what is omega? We worked out omega before, the angular frequency. It was stated to be 78.5 radians per second, and we're going to square that, and then we're going to multiply it by the mass, which the question gave as 0.05 kilograms. And that is going to give us the spring constant for the system. When we work out all of that, we should get an answer of 308.1 newtons per centimeter. And it's not newtons per meter in this case because the amplitudes that we got were in centimeter. Yeah, the period was for the amplitude in centimeters, not meters. So the spring constant is going to be in newtons per centimeter. But this is still not the spring constant of one of the springs. The question specifically said one of the springs. So how do we find the spring constant for one spring when given the spring constant for the entire system? Well, the springs are in series. What that means is that the springs are attached in a line like this. See, it's a straight line that attaches the springs like that. That's what I mean by in series. Now, the formula for the spring constant of springs in series, the total spring constant, is the product of the springs, so K1, the product of the spring constant for the springs, so K1 times K2, divided by the sum of the spring constants, K1 plus K2. Now, the springs were identical, the question stated. So, K1 is equal to K2. So, this formula basically becomes K1 equal to K2, and we're multiplying K1 by K2. When you're multiplying the same number by itself, you're basically squaring it. So, it's K squared. And then K1 plus K2, both K1 and K2 are the same. When you add 2 of the same number, you get 2 of that number. So it will be 2K. Now the K cancels out the square up here. So we're left with K over 2. So the total spring constant for the springs in series is K over 2. Which means this number here that we got is actually equal to the spring constant for one of the springs divided by 2. So if we want to find the spring constant for one of the springs, we would just basically say it would be K is equal to KT times 2. So the spring constant for one of the springs would be 308.1 newtons per centimeter times 2, and that would give us a value of 616.2 newtons per centimeter. If you wanted to convert it to newtons per meter, you would simply just multiply this number by 100. So you would get 0.61620 newtons per meter. Part D. A small lump of plasticine is fixed to the mass. On your graph, draw a line to show the possible variation with frequency of the amplitude of the vibration of the combined mass. What does that mean? Well, plasticine is like a putty-like material, and basically they took plasticine and they put it onto the mass. So what is the graph going to look like now that the mass is heavier since it has the plasticine added to it? What would the graph look like? Let's go back to the graph. So this is the graph here that we drew, and we want to find out what would the graph now look like if the mass was, well, basically heavier. Well, in simple harmonic motion, the total energy of the system is directly proportional to the square of the amplitude. Basically, what would happen to the amplitude if the energy supplied decrease? Well, the amplitude will also decrease. Now, the variable frequency generator has a fixed amplitude, which means it has a fixed energy. So the energy supplied to the system is not going to change, but the mass is getting heavier. So the energy it takes to move the mass increases, which basically means that the energy supplied is not able to move the mass by the same amount that it was before because the mass is now heavier and the energy supplied has not been increased. The energy supplied is constant. So because of that, the mass spring system would have a smaller amplitude, one that is less than the max amplitude of this. So the mass spring oscillator would have smaller amplitudes at given frequencies, amplitudes that are less than the ones that we have plotted. So what would the graph look like? Well, the graph would basically kind of shrink, or it would go underneath this graph here. So let's say the maximum amplitude is now somewhere here. I'm going to put a dot and a circle around it, like that. That basically means the graph would look something like this. So the graph underneath the one that I drew before is basically what the graph would kind of look like if the spring was weighted down with a little bit of plasticine. Now the question says, briefly describe one situation in which it is advantageous to use the phenomenon illustrated in this experiment. What phenomenon was illustrated in this experiment? Earlier on in the video, I basically said that when energy is being supplied at a specific frequency, and that frequency is equal to the natural frequency of the vibrating object, then the object will vibrate with maximum amplitude, right? Maximum energy. And that basically is a statement of resonance. The phenomenon illustrated in this experiment was indeed resonance. Why was it resonance? Well, basically, we applied different frequencies and got different amplitudes until we got to a frequency, a specific frequency that gave us a specifically high amplitude, the highest amplitude of all. That high amplitude right there is a consequence of resonance. Now, where would it be applicable to have resonance? Briefly describe one situation in which it is advantageous to show or make use of resonance. I'll give you one example. When you have bone outgrowths that are unwanted in the body, you could supply energy to the bone outgrowth, the natural frequency of the outgrowth, and you could basically shatter the bone because it would be vibrating with maximum energy and therefore it would shatter, right? And that would remove the bone outgrowth if it is unwanted. So that's one example of how you could use resonance. Resonance can also be applied to different situations, like with TV stations and magnetic resonance imaging. You can look up those if you want to and if you want to use those instead. So we have come to the end of this past paper question video. If you were able to do all of these processes in the allotted time frame, then you would have gotten near 15 marks for the question. You want to try to ensure that you're able to do these questions in a timely manner. I might take a long time to do these questions because I'm explaining everything, but in an exam, you should have some of these things automatically understood, so it doesn't take as long for you to go through the entire question, right? But that is going to be it for me for this video. Thank you all for watching, and I hope you've learned something.